So you may have been wondering, in what we've done so far, where are all these solutions coming from, right? We had solutions that involved e to the x, sine, cosine, things like that, and they basically just came out of nowhere, right? I mean, if I tell you the solution of a differential equation, you can check that it works, but the real question is, how are you going to come up with that, right? So we're going to answer that question in this video and the next for a particular kind of differential equation, that is those with constant coefficients. They're going to be homogeneous and linear, of course. I'm going to call these ConCoHomLinDEs for short. All right, so what does one of these equations look like? So here the coefficients are constant, right? So before they were allowed to be functions of x, we're still going to handle that later, but for right now we're just treating them as constants. Notice that of course we've omitted the first one, which we might call a naught, because we're assuming it's 1. Okay, the corresponding linear differential operator is d to the n plus a1 d to the n minus 1, etc., all the way down to an. And that constant term, remember, acts as a constant multiple on the function. So the term any corresponds to just this plus an at the end. And if you look at this for just a minute, you realize that's a polynomial in D. Right now, remember, D is this linear transformation, so maybe it's a little bit weird to think of a polynomial whose variable is D, but that's exactly what we're going to do. So to make us a little more comfortable, let's rewrite that with a variable r, thinking of that as a variable that maybe could stand for a number. This polynomial that we've obtained is called the auxiliary polynomial for the equation. And the equation that you check to find the roots of it is called the auxiliary equation. Those roots, in turn, are called auxiliary roots. So let's give an example where we just compute the auxiliary equation and find the auxiliary roots. So if we look at this equation, y double prime minus 8y prime plus 16 equals 0, the corresponding operator is d squared minus 8d plus 16. So to get the auxiliary polynomial, you just replace d with r. And let's write down the auxiliary equation. Notice that that factors. So our auxiliary roots are just r equals 4. And I want to observe that that occurs with multiplicity 2. Multiplicity is going to play an important role in what we talk about. Okay, so far, I've just told you, take your equation, you can turn it into a polynomial, you can consider the roots of that polynomial. What does that buy us? Well, it turns out that these linear operators act a whole lot like polynomials. If I give you two different of these operators, which I'm going to call ConCoHomLinDEs, right? So these are these constant coefficient linear differential operators. They commute with each other. So if I do q first and then I do p, that's the same as if I do p first and then I do q. This is actually extremely easy to write down a proof of. So if I have two of these operators, I'm going to write them out, call the coefficients of p a and the coefficients of q b. We're just going to write out what it means to apply q first and then apply p. Okay, so we just write out q, we write out p. Now we go ahead and apply p to q. When we do that, we're going to get a sum of terms. The first terms I've written here are the result of applying dn to each term that we got from q, and we have to do that for each of the terms of p. When we do that, we get this sum of terms. Notice they've been arranged in an n by k grid. That's exactly the same way that you multiply polynomials, right? Okay, so I'll leave it to you to check that if you do q of d times p of d, right? In other words, first apply p of d to f, and then apply q of d to that, you'll get the same thing, except your grid is going to be transposed. In fact, this isn't a coincidence. These polynomial operators act like polynomials in this sense, that is to say, to compose them, you just have to multiply them like you'd multiply polynomials. They also can be factored like you factor polynomials. Now, why do you factor polynomials? It's because you want to solve the equation that polynomial equals 0. You want to find the roots. How does that work? You factor the polynomial, you look at each factor, you find the roots of each factor. Those contribute to being roots of the entire polynomial. And this theorem says it's exactly the same thing. So what do we want to do? We want to solve the equation p of d times y equals 0, right? We want to find solutions to that homogeneous differential equation. So how do we do it? We do it the same way, the exact same way that we solve algebraic equations. First we factor. When we factor, we get lower degree if they're a polynomial or lower order if it's a differential equations. We solve those and then just throw those solutions together, and that's how we solve the whole thing. Let's do an example. So we write down the auxiliary polynomial and we factor it. So now we need to solve the following two equations. Y prime minus 2y equals 0, that comes from the first factor, and y prime plus y equals 0. That comes from the second factor. So you notice these are lower order equations. They should be easier to solve. Remember, when you're factoring a polynomial by the fundamental theorem of algebra, you can in fact always factor that polynomial into linear and quadratic factors. So let's talk about how to solve the linear and quadratic factors, and then we'll be done. So this is really just an observation, or if you like, an educated guess. Let's consider this equation, d minus r to the m of y equals 0. Right, so we've had two of those where m was 1, but you know, when you factor, you can have repeated roots. So let's do the repeated root case. So we're looking for m solutions, and here they are. So what you do is you have e to the rx. I think we can check directly that that's a solution to this equation. And then you multiply e to the rx by increasing factors of x until you get to m minus 1. What I want you to do now is pause the video and just verify for yourself that each of these, in fact, is a solution. You can also check, if you want to, that they are linearly independent by using the Wronskian. Okay, so let's go ahead and apply this theorem, or this observation, to the equation directly above it, and we'll see that the corresponding solutions are going to be e to the 2x and e to the minus x. Okay, there we go. So we have solved, from scratch, our first differential equation. Fantastic. Let's do another one. Let's solve y triple prime minus y double prime minus y prime plus y equals 0. This one you have to think about a little bit. It's order 3, so the auxiliary polynomial has degree 3, but we can factor that. So our two equations that we factor it into are y prime plus y equals 0 and d minus 1 squared y equals 0. Each of those is going to give us some solutions. That's e to the minus x, and this one we get 2. R is 1 here, so that'll give us e to the x, and then the second solution is x times e to the x. So there we go, we've got 3 solutions. Our basis of the solution set will be e to the minus x, e to the x e to the x. You can check by computing the Wronskian that those are linearly independent. That means we've got a basis because we've got 3 solutions. We have a 3-dimensional solution set.